In this video, we are going to look at giant covalent structures. In our previous video, we had a look at the properties of covalent compounds. However, now we want to see some of the giant structures. When you hear the word giant, generally here we are looking at something relatively big compared to something else. However, here we have the word structures. We are not using giant covalent compounds because we shall have a different makeup. It may not be a compound, but it will be an appearance. So when you hear structures, we are looking at the appearance of that given substance. So let's get started. So giant covalent structures can also be known as giant atomic structures. This is because these structures normally contain very many atoms. Many atoms come together to form something big, something gigantic. However, you will realize that for most of the substances we are going to look at today, for example, graphite, diamond, and then silicon dioxide, they are going to have very high melting and boiling points. When you look at the simple covalent structures, the ones we looked at previously, substances like oxygen, carbon dioxide, methane, and so on, these were actually falling under simple covalent structures, although we didn't group them into that category, but that's where they fall. And we had seen that actually these compounds had low melting and boiling points. However, for the giant atomic structures, we are going to see that they usually have very high melting points, and we shall see the reason behind that. So our first giant atomic structure is going to be diamond, and we are going to see its structure in terms of bonding. When you look at this structure here, it is representing the structure of diamond, and we have some spheres here. These black spheres are actually representing carbon atoms. Diamond is basically carbon, so diamond is an element. However, we shall see that each carbon atom, let's put emphasis on this carbon atom here in the center. We shall see that this carbon atom is bonded to 4 other carbon atoms. Remember, carbon has 4 electrons in the outermost energy level, and if it bonds to 4 others, it means all its 4 electrons have been used, because the bonds between these carbon atoms are actually covalent bonds. So each carbon atom is bonded to 4 other carbon atoms in diamond. So each carbon atom is bonded to 4 other, let's write 4 other atoms of carbon. So diamond is basically made up of carbon atoms that are covalently bonded to one another. So because of this type of bonding, carbon has no free electrons, and because of that, it will not be able to conduct electricity, because all its electrons are actually used in covalent bonding. However, because of this three-dimensional structure, carbon can form a very large structure of diamond, and in this case, this diamond will be quite hard because of the strong covalent bonds between all the carbon atoms. So because of these many covalent bonds, we shall see that this diamond is actually very hard. So as such, diamond is basically a hard substance, and it has a very high melting point. We had seen that most covalent substances actually have low melting points, but in this case we're having a covalent element. We have only carbon atoms in diamond, and it has a very high melting point of about 4000 degrees Celsius. So because of these facts, we shall see that diamond can be used in making cutting tools. So because it's hard, it can be used in making cutting tools. And maybe one other aspect of diamond, apart from making these glass cutters, is that it has a very high heat transmission capacity. It can easily transmit heat even better than silver. Even if it does not conduct electricity, here does not conduct electricity, in terms of heat it is good at conducting heat, does not conduct electricity. So there are many other uses of diamond apart from being used as a cutting tool. It can be used as a jewelry and many more. At least I made a video on properties, uses of diamond. You can please check it out in one of my playlists. So that's all about diamond. Basically the main focus on diamond will be the 4 carbon to carbon bonds, covalent bonds. So for this diamond to melt, we shall have to break these covalent bonds, and these are quite strong. That's why we shall have these high melting points. Our second giant atomic structure is graphite. Graphite, just like diamond, is also basically carbon, made up of carbon atoms only. However, the arrangement of these carbon atoms is quite different from that of graphite. Diamond. We had seen that in diamond we had one carbon atom bonded to 4 other carbon atoms. However, here in graphite, if we look at these spheres here, are going to represent our carbon atoms. However, if you look at the arrangement in graphite, we shall see that each carbon atom is actually bonded to 3 other carbon atoms. When you look at this other carbon atom here, it's bonded to 3 other carbon atoms. This one here, 1, this one 2, and this one 3. So unlike in diamond where we saw 1 atom bonded to 4 other, in this case each carbon atom is bonded to 3 other. And because carbon has this electronic configuration, if it creates 3 other covalent bonds, it will always have 1 free electron redundant. As such, these free electrons will always be moving around within this structure of graphite. So because of that, our graphite can conduct electricity. I made a detailed video about the structure, properties and uses of graphite. You can try and check it out because I will not be so detailed in this case. So because of this 1 to 3 form of bonding, 1 carbon atom bonded to 3 other carbon atoms, we shall see that we shall form a hexagonal layer or ring of atoms. So as you can see, a hexagonal means they are 6-sided. If we are to count 1, 2, 3, 4, 5, 6, and these hexagons will create what we shall call layers. So we have this as our upper layer, and then we have this other one as our layer 2. So you realize that in graphite we have different layers. However, these layers are being held or put together by weak forces of attraction, and these weak forces of attraction, we call them van der Waals forces of attraction. Van der Waals forces of attraction, they're actually weak. That's why when we apply some force, these layers can easily slide past one another. So graphite is relatively soft and can conduct electricity. However, it also still has a very high melting point of 3600 degrees Celsius roughly. So most of the covalent substances we had looked at actually had low melting points, like water melting at 0 degrees. However, for graphite, these are actually atoms, or this is an element, and it's gigantic. Because of the strong forces of attraction, the strong covalent bonds, it still has a generally high melting point. So because of its softness, it can easily slide. We can easily use it in making our pencil leads. So we just have to mix it with some clay, and then we can create our pencil leads. It's also good at working as an electrode because it can conduct electricity. So there are many other uses of graphite. You can please check them out in my other video like I stated earlier. But basically in graphite, the difference is that one carbon atom is bonded to 3 other carbon atoms, leaving behind a free electron which will then conduct electricity. Lastly, we are going to look at silicon dioxide. There are many other giant atomic structures, but I felt we need at least to look at these 3. So silicon dioxide is well known for being the chief ingredient in making of glass. So this is basically sand, and the structure of silicon dioxide is quite similar to that of diamond. Remember, diamond is mainly made up of only carbon atoms. However, in silicon, we shall see that some of the carbon atoms, if this had been carbon, with the one in blue also carbon, but in this case, one carbon atom is replaced by silicon. So the ones in blue become silicon atoms, but the structure remains the same, just that in this image here, we have an open structure, but if you can go back, you can still follow through and see the difference. So we shall see that actually each silicon atom is bonded to 4 oxygen atoms. However, each oxygen atom, which is in black, is bonded to 2 silicon atoms. So if you can do the math, you realize that we shall come up with a ratio of 1 silicon atom being bonded to 2 oxygen atoms. So this is how we come up with the structure of silicon dioxide. It's well known for making glass, like I had stated, and also being used in optical fibers. So there are many other different examples of giant atomic structures, but we shall only look at these 3. Lastly, we are going to look at our top 3 questions. Question 1. Diamond and graphite are 2 common allotropes of carbon. I didn't talk about allotropes in this video, but at least I talked about diamond and graphite both being made up of only carbon atoms. So using your previous knowledge about carbon and its compounds, try to figure out whether this statement is true or false. Question 2. Graphite is used for making pencil lead electrodes, both A and B, or none of these. Let me know in the comment section below. Then question 3. Diamond and graphite have very dash melting point. So try to identify whether they'll have high or low melting points. Thanks for watching. If you find these videos helpful, don't forget to like, share, comment, and subscribe, as well as hitting that bell notification so that you are always the first to be notified whenever I upload new content. In our next video, we are going to look at metallic bonding, another type of bonding that is quite common, just like covalent and ionic bonding. Be well.